In this tutorial, I'm going to introduce you to quantification theory. Let me give you the prelude and motivation to quantification. We've just studied a system, propositional calculus, that has a set of axioms and a formal proof theory that allows us to prove a very wide range of arguments using, obviously, the axioms and the understanding of a formal proof, like the rule of rigor and so forth. But still, there are a number of propositions that we can't capture adequately using propositional calculus, and so consequently there are valid arguments that we can't prove valid using just the tools of propositional logic, the axioms and the system of proof. Let me give you an example. Suppose we turn our attention back to categorical logic, and we look at an argument like all cows are mammals. Some cows are jerseys, therefore some jerseys are mammals. Now, if we look at this argument and we were to formalize it using only the tools of propositional logic, there's no way we could prove this argument valid. And here's why. This is a proposition. We can represent that proposition with P. This is another proposition. It's different. It overlaps in some of its internal ingredients, but superficially it's just a proposition. We could represent that as Q. And this conclusion is a proposition that also overlaps in some of its ingredients, but that's inside a proposition. And so we will have to formalize it with R. So the schema of the argument is P, Q, therefore R. And you can tell almost at a glance that this schema is invalid. Let's do a short truth table just for old time's sake, right? So here we have our two premises. We're going to make the presumption that the premises are true and the conclusion is false. Can we find a set of values for P, Q, and R that makes this assumption true? Easy. R is false, P and Q are both. That illustrates the problem that we have. And what it all boils down to is that categorical logic is very good at looking at the inside of propositions, the issues that we talked about, the ingredients, the subject and predicate terms, a quantifier, and the quality, which tells us whether we have class inclusion or exclusion. So what we'd like to have is we'd like to have a system that provides us the symbols and the power of propositional logic, but also is able to look inside propositions and analyze the way the internal parts relate to each other to generate the assertion of the proposition. And that is exactly what quantification was invented to do. It is a way of unifying the analytical tools of categorical logic, and especially the ability that categorical logic gives us to look inside propositions at the way the constituent ingredients interact with each other to form the meaning or the assertion of the proposition. Anyway, to combine those analytical tools with the power and abstraction of propositional logic. So what we're going to do then is we're going to learn how quantification theory accomplishes that goal. So let's look at the way we will represent a really straightforward proposition. Let's look at all S as P. So now remember, S and P are terms. They could stand for anything. The assertion here is a universal affirmative. That means that it's talking about every member of the set S and saying about that every member of S is included in the set P. So we have all the ingredients, a subject term, predicate term, copulative verb, a quantity, in this case universal, and a quality, in this case affirmative. Now how can we symbolize what's going on in this proposition in a way that allows us to capture that same information but is more consistent with propositional calculus. Well, here's how we do it. We think of the proposition all S is P as having two parts. It has a subject part, and the subject is inserted into a predicate, and the predicate is blank is P. So we're dividing the proposition into a subject and a predicate, and then on top of this structure, we're placing an additional symbol that tells us about the quantity. We'll get to that in a minute. So think about this. Matthew has a headache. So Matthew has a headache. Sorry about the handwriting, but Matthew has a headache can be formalized into these two parts. Matthew is the subject term, and the predicate is blank has a headache. Okay? Now, what's the usefulness of this? Well, the usefulness of it is that we can actually take this predicate as its own sort of independent thing. Blank has a headache. Notice it's not a proposition, but it is sort of a proposition ingredient. And then we could put into this proposition any argument or anything that stands for a subject that we might want. For instance, instead of saying Matthew has a headache, we could say Don has a headache or Natalie has a headache. So the value here is that it still gives us an ability to look inside the proposition, especially when we talk about the ingredient over here that tells us the quantity. But even analyzing ordinary sentences into a subject and a predicate can be very useful. So let's adopt some conventions about how we're going to do that. So the argument that goes in, and that's what they're typically called, the argument that goes in to a proposition is sort of like the domain that goes into a function. So you will remember this from our discussion of propositional calculus. That means that we can treat the predicate part of this as a function, and that's how we operate with it, okay? So instead of blank has a headache, we're going to abbreviate or symbolize blank has a headache with the symbol H, and that symbol is going to have a slot where the argument goes. And in the case of Matthew, we're going to use a lowercase m to stand for the argument Matthew, and we're going to write that in here in a way that's very similar to a function. So, for instance, f of x. We don't typically use parentheses, although some systems do, but we're not going to in our system that we're adopting here. So the idea is we're going to use a capital letter to stand for what is analogous to a function, which is the predicate. Blank has a headache, or blank is 5'11", or blank is near Austin. Those are all predicates. And then we're going to use lowercase letters to represent the arguments that we insert into that predicate to create a whole sentence. So now, knowing the difference as you do between a variable and a constant, let's think about this letter M as a constant that stands for Matthew. Similarly, a lowercase d could stand for Don. A lowercase n could stand for Natalie. And that means that we can use the predicate, blank has a headache, to represent several different sentences. So, for instance, if I wrote H of D, that actually means Don has a headache. So what have we done? We've taken what H stands for, that's blank has a headache, and what D stands for, that is the individual Don, and we have inserted it into the predicate to create an actual proposition. So notice, H of D, in other words, Don has a headache, is an actual proposition with a truth value, because the condition that the world is in right now either makes it true or makes it false that Don actually has a headache. We don't have to know whether it is true or false. All we have to know is that it is an assertion about the world that has some truth value. Now think about what it means to write this. if x is a variable, what this actually means is that there's something that should go in, some value that should go in where the x is. So x is standing for an argument, and that argument goes in a slot of the function h. So in other words, what this actually means is exactly what this means with no argument. It means blank has a headache. And why is that? Because we haven't said anything about what x is or could be or might be. So remember, because it's a variable, it's like if I said to you, I have x plus $2 in my pocket. I mean, that could mean anything. We don't know what x is, and we don't know how to assign a value to it. So h of x merely means blank has a headache, where the x is a placeholder for a value that belongs there. In other words, there has to be a domain for these things, right, that go in for x. Some things could not substitute in for x in this particular predicate because it would be nonsense. So, like for instance, if I said that my keyboard has a headache, I might say that metaphorically, but it doesn't make any sense to say that as an actual literal claim about the world, because keyboards don't get headaches. So the whole idea here is, in terms of our basic elements, is we take an ordinary sentence and we break it down into basically subjects and predicates, but subjects and predicates in a logical sense, not in a grammatical sense. And then we represent the predicate with a symbol that's more or less like a function, and we represent the slot that the argument goes in as a variable, because that could contain anything that is appropriate for that slot. And then if we put a constant that is appropriate for that slot in the place of the variable, for instance, h of n, then we've generated a proposition. So the meaning of this, given our dictionary here, is Natalie has a headache. So what we've introduced here is some of our basic ingredients. We've got the subject of the proposition, and we've got the predicate. The predicate serves more or less the role of a function, and the subject serves more or less the role of an argument. A function and its argument is either a schema for a proposition, like h of x. That's a schema because it's not a real proposition, because it doesn't have a real value in for the argument. So we don't know how to assign a truth value to it. We don't know how to. That's different than we don't know what the truth value is, right? So let me illustrate this. H of x is a schema for a proposition. It means basically blank has a headache. But h of m is an actual proposition. Matthew has a headache. Now, you may not be in a position to know whether Matthew has a headache is true or not, but you know how to know things like that. We have some effective procedure for determining the truth value of a proposition, or at least in theory we could have an effective procedure.
In the next tutorial, we'll build on these elements and see how we can formalize more complex propositions, combining the elements that we've just learned from quantification and the operators from propositional calculus.